For this talk, we give an overview of the Sylow theorems. Proofs of the Sylow theorems are rather technical, so we'll save the proofs for another video. For here, we just want to get an idea of the philosophy behind the Sylow theorems and take a look at a few examples. Now, we have a group action, of our group G on itself by conjugation. So, from that group action, we had conjugacy classes and the class equation, and in turn that led to Cauchy's theorem. Cauchy's theorem said if we had a prime that divided the order of a finite group, we were guaranteed to be able to find an element in the group of that order. The Sylow theorems are going to be the analog of Cauchy's theorem for subgroups. Now, the idea is we're going to change the set that the group acts on. So we're still going to have conjugation, but instead of acting on elements in the group, we let conjugation act on subgroups in the group. Now, with this group action, so our set X is now going to be H, all H subgroups in our group G. The action is just to take the element G on the subgroup H and conjugate. So if I conjugate, we get another subgroup. Now, because we have a group action, we could just run everything through our machinery for group actions. So immediately we have a partition on the set of all subgroups in H. That partition is going to let us write X as a disjoint union of the orbits. So here we're just going to pick one representative per orbit or equivalence class. Each orbit, we just pick subgroup H, and we're just going to push it around by all elements in the group. So this is going to be a set of all GH, G inverse for all G in the group. Now, if we have a finite group, we have a rule for the cardinality of the orbit. That's just given by taking the order of the group and dividing by the order of the stabilizer of the element H. That's going to be the normalizer of H. So let's just see that by running out the definition. So the stabilizer, for subgroup H, we'll take all G in the group that leave the subgroup H undisturbed under the group action. So there we're going to have that GH, G inverse is equal to H, and note that's the definition for the normalizer of H. Some things we should note. First, H itself is always a subgroup of its normalizer. And if we have the H is normal in the group, then the normalizer is going to be the entire group. So you'll note before where the singleton classes were the elements of the center of the group. Here the singleton classes are going to be the normal subgroups. Now, when G is finite, we have a class equation for subgroups. The number of subgroups in the group G is equal to the number of normal subgroups. So we split off all the singleton classes plus the sum of the orders for the non-singleton classes. Here we have one representative per class. Now, as written, not very useful, but there'll be versions of this which will be useful. For an example, let's consider S3, the symmetric group on 3 letters. This has 6 elements. It'll also have 6 subgroups. So we have the identity subgroup, the group itself, 3 subgroups with 2 elements, 1 subgroup with 3 elements. The normal subgroups are going to be the identity subgroup, the group itself, and the 3-element subgroup. So this is normal by the index 2 theorem. Now, if we check our cardinality rule, first we note how conjugation works. One permutation on another, our conjugation rule. So if we have this permutation, A, B, whatever going to C, if I conjugate by the permutation sigma, we leave the cycle structure alone and we just relabel according to sigma. So this would go to sigma A, sigma B, whatever, to sigma C. We first consider the subgroup given by the identity and the element 1, 2. If I want to know what subgroups are in its orbit, first we'll count, so I have to compute the normalizer. Using the conjugation rule, okay, well, the identity has to get sent to itself when we normalize. This other element then has to get sent to itself also. So we need to find all permutations that send 1, 2 to itself. So either the identity, which sends 1 to 1, 2 to 2, or the switch, 2 goes to 1, 1 goes to 2. So there are 2 elements in the normalizer. Cardinality rule says we have 3 elements in the orbit of this subgroup. Those orbits, when we use our conjugation rule, okay, so what do? Well, we can send 1, 2 to 2, 3. Okay, so 1 goes to 2, 2 goes to 3, 3 goes to 1. And we can relabel to get identity and 1, 3. So 1 goes to 1, 2 goes to 3, and then 3 would go to 2. So that checks cardinality rule. Note, okay, using this class equation, we have 6 subgroups. We have 3 normal subgroups, and then 3 elements, 3 subgroups in the other class. If we look at the 3 element subgroup, okay, it's normal by the index 2 theorem, but it'll also be normal according to our conjugation rule. So no matter how we relabel these elements, we're just going to get back the same 3 cycles. So normal. So normalizer is the group itself. Then we're going to have a single element in its orbit. Here are the Sylow theorems. Recall, these are supposed to be an analog to Cauchy's theorem for subgroups. Now, we have a finite group G. We'll write the order as P to the K times M, where P is a prime, P and M are relatively prime. So here I'm splitting off the highest power of P in the order of the group. Sylow theorem 1 says, there exists a subgroup P of order P to the K in our group. If we have any subgroup of that order in G, we'll call it a Sylow P subgroup. Sylow theorem 2, all Sylow P subgroups are conjugate. So if we think in terms of the group action, Sylow P subgroups form their own orbit. Then we have Sylow theorem 3, which says, okay, the number of Sylow P subgroups, we'll denote that n sub p, is congruent to 1 mod p. So this is going to give us a restriction on how many Sylow P subgroups we can have. Now note another way to write this is p divides n sub p minus 1. For convenience, I'll put 2 other helpful rules for calculating n sub p here. We have the n sub p divides the order of the group. That just follows from the cardinality rule. So n sub p, the number of Sylow P subgroups, using 2, is equal to the order of the group divided by the order of the normalizer of P. So that means we have n sub p as a divisor of the group. We also have that P does not divide n sub p, again from number 2. So to see this, note, again from the cardinality rule, n sub p is equal to the order of the group divided by the order of the normalizer of P. P is a subgroup in its own normalizer. So P to the K divides the order of the normalizer of P. Now when we take that quotient, we're going to cancel out this P to the K in the numerator and denominator. So what's left over is going to have no factor of P. So P is not going to divide n sub p. For an example, let's consider S3 again. So here the order is equal to 6. Possible primes are 2 and 3. If we use rule number 3, possibilities for Sylow 2 subgroups are going to be 1 or 3. Possibilities for Sylow 3s are going to be just 1. So we've already seen that we have 3 Sylow 2s and 1 Sylow 3. Now, an important point here, if we have some n sub p equal to 1, that means associated Sylow P subgroup is going to be normal in the group. This follows because we have a unique subgroup of a given order, so normal. For another example, okay, let's consider A4, alternating group on 4 letters, or rigid motions of a regular tetrahedron. I'll list all the elements in permutation notation. Okay, and I'm grouping the elements so that you can see the subgroups. All you need to do is add the identity element. So here, order of our group is 12. So the divisors are going to be 2 and 3. The number of Sylow 2 subgroups. Okay, you have to be careful here. This subscript does not tell you the order of the group, it tells you the prime. So our Sylow 2s are going to have order 4. We have either 1 or 3. For the Sylow 3s, we're going to have 1 or 4. So we see 4 subgroups of order 3. We have 1, 2, 3, 4. And 4 subgroups of order 4, we have just 1. Okay, and we note this one here is going to be normal, which we've seen before. One drawback to the Sylow theorems. They say nothing when our group is a P group. That is, when the order of the group is a power of a prime. So for instance, if we take the quaternion group or the dihedral group with 8 elements, they have order 8, so Sylow theory doesn't apply. Now that's not a problem. P groups have nice properties all in their own right. So for one, P groups are always nilpotent. We won't say anything about that here, but we will note a strong analog to Cauchy's theorem. So if we have a P group, so let's say its order is P to the K for P of prime, there exists subgroups P sub I of order P to the I for all I between 0 and K. So Lagrange's theorem would say, okay, these P sub I are going to be the possibilities for subgroups, and this statement says that we're going to fill each possibility with a subgroup. Now, we could also enhance Sylow theory by carrying this result over to our Sylow P subgroups. To show this, we'll use induction on K, the exponent. Now, K is equal to 1. We have P elements and our group is isomorphic to Z mod P, and it's clear that the result holds here. For the induction step, we'll assume our statement's true when K is less than or equal to N. We want to show it's true when K is equal to N plus 1. So we have a group whose order is P to the N plus 1 with P of prime. The class equation says, okay, if we have a group with order P to a power, its center is going to have more than just the identity element. So its order is going to be P to the J with J greater than or equal to 1. Cauchy's theorem says, since P divides the order of the center, then there's going to be an element in the center with order P. So we'll call that X. Now, if I take the subgroup generated by X, it's going to be isomorphic to a Z mod P, and because X is in the center, it's going to be normal inside of our group G. With that, I could form a quotient map from G to the quotient group G mod H. So we're just going to send each element G to the coset GH. Now, if I count the number of elements in G mod H, it's going to be the order of G divided by the order of H, so I'll have P to the N, and our induction hypothesis applies. So in G mod H, we're going to have subgroups of order P to the I for all I that apply to G mod H. Now, if I want to get subgroups in G itself, what I can do is just take the inverse image of these subgroups under Q. So what happens there, when I take the inverse image, we're just going to notch up the order by 1. So if I take the inverse image of P sub I, that's going to have order P sub I plus 1. Now, when we consider all of these, we're going to have, okay, all possibilities filled except for P to the 0, which is just 1, and that's filled by the identity subgroup. So all you need to get our result is to show that under homomorphism, the inverse image of a subgroup is a subgroup of the domain group.